Awesome. Well, fantastic. Thank you for the introduction. My name is Morgan Quigley. I'm with the Open Source Robotics Foundation. This talk will be about kind of a brief overview of ROS, and then we'll dive into some technical details and do some demos along the way and maybe watch a robot movie or two. So this talk is about ROS and friends. We're from the Open Source Robotics Foundation, so what we do, we support the development, distribution, and adoption of open source software for use in robotics research, education, and product development. That's very broad. We can fit a whole lot of things in there. That's our website, OSR Foundation. We have the little building there in Mountain View, California, out in Silicon Valley. Okay, so the big picture here, what we're hoping to recreate and hoping to help occur is the creation of something like a LAMP stack, but for robotics. So the LAMP stack, I'm sure there are many people here in this room who have made critical contributions to it. Linux, Apache, MySQL, Python, Perl, PHP, something other scripting language of your choice, can produce .com prototypes now. And so if you have an idea for a great new .com, you can go download LAMP stack, code for a bit, and then before too long you're going to have a prototype up and running for not that much cost in time. It's to the point now where that's just a standard thing. You can go on any number of cloud providers, download a LAMP stack image, get it up and running on a virtual machine somewhere really quickly. In the robotics industry, there's historically hasn't been a sort of an analog for that, where if you wanted to get a new business or a new application up and running, it was a lot of sort of pain and suffering of getting these pieces to work together. So what we're trying to do is to push a bunch of subsystems here and components and kind of glue them or duct tape them all together with ROS to let prototypers and entrepreneurs, whoever wants to, that has an interesting idea for a robotics company, to be able to get their prototypes up and running quickly and then move it to development and production. So these are some of the open source projects that we're working with and we're helping to combine into a unified system. I'm going to talk a little bit more about them in turn here. So let's step back a little bit and look at why robotic software is hard. In other words, why is this difficult to do today? You can look at the first line of that thing there is just a little cartoon. When I was at Stanford, we used to call this the fetch a stapler problem, and it was sort of an inside joke of if you have some really simple task, like if you want to tell a robot to please go get me a stapler from my office, if you then break down the subtasks of that task, there's a daunting amount of code you have to write and subsystems you have to debug and integrate. So if we just start from left to right on that top row, we have corridor navigation, so you need to drive down hallways to find the right place. You need to open doors. There's a robot opening my old office door there. You might need to transfer between floors. So there's a robot in front of the elevator doing a precision laser scan of a wall so it can find out where the call button is to push to call from an elevator. Then once you get to the actual desk or table where there might be a stapler, you then need to sort of park there and look all around with cameras. The robot is trying to identify a stapler among all the sort of debris on my old desk. And then you finally need to pick up the stapler, and then you have to repeat that whole thing backwards to go back and deliver the stapler. So even something silly like please give me a stapler from my office, if you break that down, it's an incredible amount of software systems that have to work together on the robot. So for each of those little boxes there's a whole team that takes, so that just that computer vision component expands to the second line. So all those people were working on that in our lab at Stanford. That lab at Stanford was one lab among many universities across the world working on many subsystems of robotics. So that gets, again, multiplied out, the next layer of the pyramid. And then finally, what we want to have are these systems that are reusable so that you can take a subsystem that works on one robot, if you then go to the other side of the world, totally different robot, and make that subsystem work again. So the other interesting thing about robotics is it needs to be fast and it needs to be debuggable because we have these huge teams working on these problems that sort of at the core, the difficult problems in robotics involve uncertainty, which means sort of every run of the robot you're going to see a lot of the different intermediate calculations, and so being able to record these and play them back and have real data sets is critical. So another interesting thing of robotic software, oftentimes it turns into a distributed systems problem. So this was one of the stair robots we had at Stanford for many years. It's sort of a prototypical big type battleship robot, whereas it's a mobile base on bottom, a bunch of big batteries, a bunch of lasers pointing everywhere. It had 3 onboard computers, a manipulator arm, a whole bunch of other sensors. Then I would typically walk behind it with a laptop, and then there would be a rack of servers in the basement that is talking to and streaming data to and from. So not only are they tricky programming problems, but then I have the distributed systems aspects as well. So these are tricky problems. A little bit of backstory for ROS. So I had these things. I was a TA at one time of a robotics class at Stanford. We had lots of different student groups coming together for problems like that fetch a stapler problem, where we wanted to enable everyone to debug their systems in little small groups, and then periodically all the systems kind of come together and would do these big demonstrations. And so I was trying to support that. I wrote a few prototypes there. One of them was called Switchyard. It lived for maybe a year or so. Brian Gerke, who many of you may know, was on the player stage. He ran that for a long time. Eric Berger was also one of my classmates at Stanford, and then it went to Willow Garage, and then Ken Conley at Willow Garage. We all had a whole bunch of different experiences and projects we previously ran. We kind of threw them in the blender for a couple years, and out came this ROS architecture, which I'll describe here. There have been, of course, since those contributions, many contributions by many dozens of other people to the core of ROS, and then many hundreds and thousands of contributors to packages that sort of surround ROS now. So it's helpful to first perhaps define what ROS is not. It is not a real OS, and I say that on purpose because I know many people in this room are deeply involved in the Linux operating system internals. So it's not an OS. It's not running actually on the bare bones of the computer. It's one level up from that. So it's an abstraction layer that sits above real operating systems and then ties them together on the network. It's not monolithic. There's not a big IDE. Instead, it's a whole bunch of small tools that get tied together. Oftentimes, you see people working on ROS. They'll have 20 terminals open on their machine, and it's not tied to any particular robot. That robot there is the Willow Garage PR2, which many people have probably seen videos of that robot. Willow Garage gave many of them out to labs across the world, and so there's been tons of ROS code written for it. But there are also many other platforms using ROS right now. I'll talk a little bit more about that coming up. So now what ROS actually is, it is we can divide it into 4 main topics to discuss here. The first is it's a set of plumbing, so a message passing layer. It's a set of tools, so the small tools, you can use them. Many of them are command line tools, some of them are graphical tools. It's then a collection of capabilities. So now these are big subsystems of robots. So for example, a navigation system, an image processing system, speech, spoken dialogue systems. There's a whole bunch of each of those things. So there are multiple, image computer vision systems you can go download from various labs across the world. And then it's finally an ecosystem of many people contributing to this. So I'm going to talk about each of these 4 things here in a little more detail. So first, I'll talk a little about the plumbing inside ROS. The paradigm is mostly anonymous publish subscribe. That's used in many systems across the world. I'm sure many people in this room have used that. Sometimes the terms are different, the nouns and verbs are different, but the idea here is that you have a bunch of consumers and producers of data. They can exist anywhere on the network. When one producer of data calls a publish function, then that message gets serialized, blasted out to anybody else who's subscribed to him. There's a master node that sits on top that just sort of keeps track of the whole thing. It functions much like DNS over the internet, where publishers can advertise with them. That master maintains data structures which keep lists of each person. The subscribers then sign up for data topics they want to listen to, and they receive back a list of their peers. And then all the connections are actually done peer-to-peer, so the heavy data flows, high traffic things are all peer-to-peer. It scales, so let's see. The main point we're doing here is we're connecting data streams, not actual programs. So in a ROS program, if you're writing, you would say that I want to subscribe to images. You don't necessarily write, I want to subscribe to camera 0 or camera 1 or camera 2. You say, I just want image 1. And then it's up to the system to figure out who's actually producing image 1. It tells you where to connect to that, and then all this stuff happens at runtime. So the Peer 2 robot, when it starts up, it forks off 56 ROS processes, which then in turn spawn off 538 topics, and there's a ton of peer-to-peer connections that happen. This picture was actually the sort of fetch a stapler or canonical challenge problem. There's the ROS data flow diagram. And then the main thing here is that any time that's a dynamic structure, it's not a static graph. So you can run more programs, start more terminals, run some more programs. Then now these little green nodes on the upper right would start, and then they'd connect to the system. And at any time, any of those, each bubble there or node is a Unix process. Anytime they can go down, their links to their peers obviously disappear, but then you can relaunch them, restart them, and they connect to their peers again, and everything keeps running. The idea behind that is oftentimes when you're working on a big complicated robot, if you typically aren't debugging the whole system, you're just debugging one little bit of it. So imagine that you're trying to work on the image processing or image vision part of it. You don't want to necessarily have to restart the whole ARM controllers or the navigation subsystem every time you want to change one line of code in the computer vision system. So what you can do is you can have this whole system up. So you say you have 50 or 100 processes running on the robots, multiple computers on the network. If something's going haywire, you can kill that single process, change the line of code, recompile, run it again. It'll inject itself back into the running system, and all the peer-to-peer connections come up. So the actual messages that are flowing, we have our own interface description language. We tried to keep it simple. The left line there shows this is the actual code of the ROS joystick message. So if you have a joystick and you want to control a robot, this is kind of what flows across the network. So there's just a header. All it is just basically a timestamp. And then there's a vector of joystick axes and a vector of buttons. So that's just 3 lines of code. That's literally the total of the joystick message in ROS. Then when you type make, it then blasts out language-specific implementations of all the languages that are included in ROS. So if your system had these 5 languages installed, it would then generate 1,000 lines of code of just terrible, terrible code that we should never write. It's just mind-numbing type stuff to do all those mem copies and things, and actually prone to errors, as I'm sure we've all done before. Okay, so now that's been a lot of talking, a lot of slides. Let's show some demos and have some more excitement here. So, okay, so the first thing we start in a ROS system is called ROS core. It actually used to be called bot herder, and then a large defense contractor wrote us an email and said, you know, ROS is fun, but please don't call it bot herder. Our security people don't like seeing things called bot herder in our networks, sending and receiving data to random sockets. So now it's called ROS core. That just sits in the back. That's the master program that's running on top. You think of it like DNS. So that's going to just sit there and run the whole time. We can then launch a little program called Talker, which Talker does nothing other than 10 times a second. It creates a string with hello world plus an integer, and it sends it across the network. So Talker's just sitting there working hard. There are lots of tools in ROS. One of them that's kind of fun is called RX Graph. What this does is it connects to the master node, and it says what's happening on this system. So you can see that's what's happening. It's not very exciting yet. There's the Talker node. He's just sitting there. No one's listening to him. So let's get a new shell and launch a listener. It'll be more exciting. So now this thing fires up. All it's doing is it's listening to a data topic named chatter right here. And then it is printing out whatever comes across chatter. So this is saying, you know, I heard this message. Thank you. So that's fun, but the point of the system is that this whole thing is dynamic. So we can keep injecting more nodes into the system. So let's say there's something called Talker 2, which is doing the same thing as the other Talker. We can see now as we inject him in, we'll see it pops up, gets connected in there. So now the data topic chatter is being broadcasted by 2 nodes to that listener. We can then keep repeating this, and it's kind of fun. Let's make another listener node. So now the graph's getting a little more complicated. There are now those 2 guys broadcasting chatter. There's 2 listeners. You can see the data flows starting to get a little squirrely. But then up here, there are 2 sequences of numbers now that are flying because we started those talkers at different times. So there are more command line tools. The graphics one is fun, but of course I know lots of us like to be on the command line all the time. So we can type in a topic, a thing called ROS topic. So we can say ROS topic list. And this gives us 3 things. These bottom 2 are a rough equivalent of standard out for a distributed system. So every ROS node can broadcast to something called ROS out, and you can have one terminal that collects kind of all the outputs of the systems on the network. But the one we're interested in there is chatter, so we can say ROS message show, ROS topic info chatter. This will interrogate the system and say, what is this thing called chatter? What's happening? It says it's the data type there is standard message string. There are 2 guys publishing it, 2 guys subscribing to it. So another thing we can do now is ROS topic echo chatter. And now this is going to broadcast everything coming across that chatter topic. You can see down here at the bottom, it injected a new one to the graph, ROS topic, and then a whole bunch of numbers just to make sure it's unique. Okay, so that's kind of the basics of the plumbing. We've tried hard to make this simple. It's not the world's fastest anonymous publish subscribe implementation by any means, but we have tried to make it so it is simple to do. So let's see. If we look at the minimal code here, this is the C++ version, which of course tends to be more verbose than nicer languages like Python. But the idea here is really you're just bringing the ROS node up, declaring that you're going to publish data, doing it 10 times a second, and you just sit here and spin in this loop. The other thing to note here is that we're not trying to take over your main function. There's still a main function. You're still in control of this loop. You can do other things such as run graphical interface updates or any other things that you need to do. In general, the ROS philosophy is to try not to take over your program execution. We try to make it so that you can graft your interface to the ROS on top of an existing system. So we're not trying to sort of take over the software world. We're just making these shims easy to write so that you can take an existing piece of functionality and then write a little shim around it and bridge it into a ROS system. Okay, so these guys are just publishing to their heart's content here. Let's stop them. Okay, so you can see as I was tearing that thing down, now we're just back to the single talker, which is kind of lonely. And then it's going to get even more lonely here. It's just an empty set. That's sad. Let's close that down. Okay, so back to a few more slides. That's kind of the overview of the plumbing system. That's not very exciting, so let's move on. The tool set now is where things get interesting. So we have all these different messages that we have in the system. There are thousands of them out there. So these are two of the most useful ones. The laser scan is a common thing in robotics. You'll see there's like a spinning laser. It spins around typically in a plane and tells you the distance to various objects as that laser is rotating through the world. So all of them kind of are, roughly the same. There's a thing on the top that spins around, and then they output typically a custom binary message. So this is a picture of 7 laser rangefinders there. They all have their own custom binary protocol. The nice part, though, is that now everything has been bridged to ROS. So all these things output laser scan messages. So if you turn it on, you start up ROS, start up the laser driver, you're going to have laser scan messages coming out, which is general enough to be able to define the output of all those scanners. Similarly, for the robots down there, those are a whole bunch of robots made by a whole bunch of different vendors. We just heard from Alden Brown Robotics making the Now, that one second from the upper left. They have pretty much any robot will output some sort of a representation of its state, which in robotics terminology, that oftentimes means a vector of numbers where one element in the vector per each angle of the robot. So if they were here talking about the Now with 25 degrees of freedom, the Now is able to publish a joint state message which has just a vector of 25 numbers in it. So every robot now that is interfaced to ROS broadcasts that same kind of message, which the exciting part is now you can write tools which operate one level up and that are abstracted across robots. So you can now write tools for laser scanning, visualization or map building or what have you, or robot configuration tools that are general across robots and across vendors. And that repeats for many other aspects of robotics we'll show here in a little bit. Some other tools that are very useful, the system visualizer, I was showing that RX graph. There are a collection of other tools. Plotting tools, you can take any number and send it to these plotting things, which will create what looks roughly like an oscilloscope, a time series of a bunch of different vectors. There are several simulators which have been bridged to ROS. I'll show some examples with Gazebo at the end, but there are other ones also. Then diagnostic systems where essentially that creates a GUI layer or something that's easier to put like in a desktop type notification tools, which says if all the robot is happy or not, or what the time series is of these failures. There's also a lot of tools for collecting log files. So one of the challenges of robotics is that it works great in your lab, and then you go to do a demo and it doesn't work. This sort of happens like all the time. Oftentimes you then want to, after that demo's over and maybe you survived it, maybe you didn't, you want to then see like what on earth happened to the system and why did it fall on its face right when the boss walked in. So what we're doing there is you can take the whole system and you can there's a program called ROS bag. The idea there is it's just this giant bag and all of your messages can fly into it. You can collect it, we call it a bag file, just these gigantic files of all the messages that were broadcast on the network. And then you can play them back. So you can essentially dump that message bag upside down, shake it at the right frequency so all messages dribble out right. And the rest of the system has no idea of what just happened. So anything downstream of the actual producers of those messages, it doesn't change anything. It just looks like the same system was happening. It doesn't realize that it's essentially a time warp to last week or whenever the bag file was recorded. So let's show some more demos now of more robot-specific stuff. Okay, so there's a simulator here called Stage, which is a very simple simulator. Maybe some people up here have used it. It's been around for quite a while. Brian Gerke and the Player projects spent a lot of time writing this. So the idea is sort of like Pac-Man. This is a top-down view of a world. This is actually the Willow Garage campus here, they're building. So there's a little robot here, this little blue dot. The red thing is just kind of a brick in the world that we can drag around. Okay, so we can now simulate it. You can see, a little hard to see maybe, but the blue, the kind of pale blue is the laser scanner that's being simulated. So you can take this poor robot and drag him around. But what's fun now is we can look at, see what's happening in ROS. So we go ROS topic list. So there's a whole bunch of interesting topics now. We have the base pose, which is essentially the odometry of the robot of where it thinks it is in the world. Oh, sorry, that's actually, that's how you cheat. So that's actually where the robot truly is in the simulator. This one down here, odom, that's the actual odometry. So odometry in a robot is when every time the wheel turns, it keeps track. There's usually a piece of hardware in a robot that counts how many ticks the wheels have turned. And so if you make assumptions such as the wheels don't slip and the tires are the same size, you can then integrate that and get a position estimate. Let's see this command velocity topic. Let's type in ROS topic info command vel. So that tells us that stage is, that's our simulator subscribing to it. It's of the type geometry message twist, and twist is sort of a mechanical engineering term to mean how you can tell something to move. Let's see what else is interesting here. So base scan is a simulated laser, so we can type ROS topic echo base scan. Oops. So now it's going to dump out a whole bunch of numbers. All those ones are just the intensity, which says it's always a full intensity reading on the simulator, but all these crazy numbers are just the ranges to the nearest objects. These are all just being blasted out by the simulator. Okay, so now let's type in this. We'll get our robot to start driving for us. So now we can see this guy is just cruising around. We can just drag him ruthlessly around here. But he's just going to kind of sit there spinning around. And then we can do some other things. So now let's see. Okay, so now this says it's of type sensor message laser scan. And again, all this stuff is dynamic, and on the fly in the system, we can interrogate these things and insert interesting things. So let's say we want to find out what that actually means. So we can say ROS message show. So now at runtime, it just connected to it. It said, please describe the laser scan message. And we have all these fields in it. So now we can say, you can just echo some of them or plot some of them. So ROS topic echo. And now it's blasting it to the screen. All the numbers are changing because as the robot is driving, the profile return to the laser scanner is changing also. So the point is this whole thing is dynamic and adjustable on the fly. You can inject whatever you want to on the command line. Okay, so let's move on. I talked at the beginning about ROS also having a bunch of capabilities. These are essentially canned features you can use out of the box. Everything's open source, of course, but it's oftentimes nice when the experts that wrote this capability wraps it up for you in something in a bigger black box. So there's several mobility systems in ROS, meaning that you can take a robot, put it down on a planar surface like this nice flat floor here, and it will drive around, make a map of its surroundings, and then you can look at that map and tell it to go from point A to point B, and it'll be able to do that. There are several systems in ROS which can do that out of the box. Manipulation, there's several, of course that's an open area of research, but there are several subcomponents of that problem that have pretty good solutions out of the box that are in there from various institutions and labs. And then perception is sort of one of those holy grails of robotics to understand the world, but there are, again, sub-problems that have pretty reasonable solutions like stereo vision. If you have two cameras and you want to do a 3D estimation of the world in front of you, there are pretty decent solutions for that that are out there, and the state of the art is wrapped up inside ROS here. So let's just show some movies. It's been a long time on this talk, and I haven't shown a robot video yet. So let's play some. Okay, so this video was compiled by Willow Garage a few months ago. So there's going to be really fast, just tons and tons of different robot platforms. They're all using ROS. The interesting thing to note is that they're doing all sorts of different crazy things, and each robot is quite different. So we've seen tracked robots now, wheeled robots, manipulators, field robots outside where everything's kind of slipping and sliding. There's kind of a car-like machine. So oftentimes what's happening on these platforms is there is a real-time layer operating beneath ROS. Like they discussed on the Now, there's an RTOS and a different processor that's running, but ROS can sit on top and help with the perceptual systems that are quite general and applicable to many different robots. So some of these kinematics are wildly different, like that platform. There's a Now with a laser on its head. Oop, and then this was doing more footstep planning. Again, ROS isn't running on the Now, it's sitting on top and being bridged to it using the layer they described. These are kind of a collection of small robots. That's a turtle bot, which I might talk about in a bit for a low-cost platform. Robot soccer is always just awesome. These are industrial arms. I'll talk more about this also, but this is a totally different world from what we're in terms of reliability. They emphasize durability on those systems much more than typical research. So this is an interesting project over at UC Berkeley, folding towels. It's been a YouTube hit if you've seen that one. Okay, so this kind of could go on forever, but the idea is there's lots of different platforms using ROS for various purposes, and then a lot of the work that's done can then be put on other robots, even if they're wildly different. Some of the subsystems can generalize quite well. Okay, so the ecosystem, we saw lots of robots. Here's to kind of categorize them a little bit. The top row there, I like to call them big bots or battleships or whatever you want to call them. This is sort of the thing we dreamed about as kids that we all still dream about and is just so awesome, which is like the robot that does your dishes and folds your clothes and picks up your room and stuff. They're large human-scale platforms. There's some form of mobility with them, typically 1 or 2 arms, one or more computers on board, a sensor head, very rich platforms. That's kind of what we designed ROS for originally. But now we've been seeing that we can port it and we can do much more than what we had originally thought with it. There's a whole other class of smaller robots, oftentimes that are much lower cost also, which is great. Then that third line there, industrial robots, is an interesting thing people are doing now. Industrial robots are totally different from research robots. They're made so that you can buy this thing, you turn it on, you set it up in your plant, and it runs 24/7, 365 for like 20 years without ever going down. So they're built with extreme longevity and reliability in mind because these are on long production lines. If that arm ever breaks, then the whole line has to stop, and it's like a total disaster. So they really emphasize durability, which means that they don't want us to just open up the control box and like start running random Linux programs on it. And so oftentimes what's happening there, this ROS Industrial Consortium, they're writing bridges between ROS and the certified real-time controllers that run these large robot arms. There's been some interesting work with vehicles at some level using ROS. Oftentimes there's, again, a hard real-time safety layer that runs beneath, but ROS is used to tie in lots of perception research to run on top of the system. Then those lawnmowers on the right are some of my favorite. There's an Institute of Navigation that runs a lawnmower autonomous competition every year. So they do precision GPS navigation research, but then the end of the demonstration is you then use it to cut a lawn with like sub-centimeter precision, which is pretty awesome. And then people are also using ROS now to do aerial platforms and water platforms, and there's even some features of ROS have been used on a surfboard, which is fantastic. Okay, so the ecosystem goes kind of around the globe. This is just a map of some self-reported locations of people using ROS and publishing code. So there are lots missing on here, but it's an interesting mixture of academic institutions, corporate research labs, companies, and individuals and amateur groups as well. This graph shows, a little hard to see the numbers there, but the self-reported public code repositories, these are things like on GitHub that have something to do with ROS. And when we look at our server logs and stuff, I know it's probably all of us in the open source world have this problem. It's hard to know how many people are actually using your thing because we don't have customer lists or anything like that. We sort of estimate 100,000 users or so at any given time. Many of that is students, so it's kind of rotating through. But that's kind of the rough estimate at any given time. That's again, it's really tough to get a hard number on that because we have mirrors in Europe and Asia as well as the main servers in the US, so that's the ballpark anyway. On the web, we're trying to help people by, there's a massive wiki at ros.org, which is, like all wikis, it's a little bit kind of wild, but you can search and typically find things of interest in there. There are also tutorials about how to just get out the box, how do you download some things, install it on top, and then do some tutorials like how you get a navigation system up. We also are running this answers.ros.org site is a community maintained site. I think these type of question and answer sites are very popular now. There are a lot of people who know a ton about robotics and ROS that are on there, and so of course, hopefully people search for their question first and find something, but if they don't find it there, when questions get asked, you find pretty good answers pretty quickly. So adoption. This was an interesting thing to look at. We're trying, of course, like everyone, to reach out and get always a bigger audience and have our work be more relevant to the real world. We are hoping to of course, to follow the curve of Linux, like everyone is. You know, the first column there is kind of when the market is grad students. We have extreme pain tolerance. You know, if it doesn't work, that's fine. If it's not documented, that's fine. If it's like backwards and upside down, that's fine. You know, eventually Linux became much more broad and easier to use. Throughout the 90s, the easy-to-use distributions that, you know, everything sort of worked out of the box, like Red Hat and Debian, SUSE. Others, many in this room, I'm sure, have contributed to those. So there, at that phase, you know, a competent professional or amateur programmer can then download it and, with some pain tolerance, get things up and running. The goal, though, of course, which Linux has now achieved, is when the general public uses the system, oftentimes without even knowing what it is. That's a picture of my dad. He has approximately no pain tolerance for technology. You know, he likes to go to a website and read the news or whatever, and he doesn't know or care that Linux is running that website. He likes to have an Android phone and have the phone work. But, you know, he doesn't know or care that Linux is running behind that. Similarly, we hope, you know, at some point to get ROS toward that thing, toward the point where people who are using systems which are running ROS underneath, and they don't know or care that it's there. That's kind of the long-term goal. So to get there, we, you know, have identified we need to support all these phases of the pipeline of how you get things into the real world. So there's the research phase, which historically has kind of been where we have been. That's a fun project at UC Berkeley that does all sorts of interesting perception research about how you fold clothes, which turns out to be enormously difficult because, you know, it's deformable. So it's like a towel, as you're in the process of folding it, turns into all these weird shapes. And when it's all clumped up in your dirty clothes bin, it's all just this crazy shape. You have to sort of pick things up and shake all the folds out. They do great work on that. That's kind of the research phase. At some point, you know, things that are promising, companies are willing to pick them up and invest development dollars into them. So right now, Toyota is doing this interesting project called the HSR platform, which is trying to be a home healthcare, home assistance to people. So now that they have different needs from the research community, because instead of the latest whiz-bang, they actually need to have, you know, stable development targets, things that don't sort of change underneath them as everyone's working. And then finally, the products. So that picture there is a company called Rethink Robotics. They're in the US and producing, that robot is called Baxter. So it's an easy-to-program robot for factory automation. The idea there is that you shouldn't have to have a PhD in robotics in order to be able to program a robot to do something in your plant. And so what they're trying to do at Rethink Robotics is make it so that you can kind of guide the robot's motion and then push some buttons on its wrist and then have it do it over and over again with some computer vision capabilities baked into it. So they're using ROS at some level underneath their software. And the great thing about it is when they sell their robot and someone starts using it, that person doesn't know or care that any bits of ROS are inside of it. And I think that's great. And that's something we're hoping to support more, is just when it gets in the public and it just works out of the box for people. So another use case, which I'll show some demos of here, is the DRC. This is the DARPA Robotics Challenge. It's a big deal right now in humanoid robotics, because what they're hoping to build are these systems that can go into partially degraded structures and essentially save the day. So this is motivated by the Fukushima disaster and other nuclear problems, where there've been, of course, with perfect retrospect, you take 6 months to analyze what happened. If there could have been a Superman that walked into that facility and knew which valve to turn and walked over to it, turned it, then the disaster wouldn't have been nearly as serious. So this is an effort to try to develop that kind of capability of a humanoid robot, human scale, human strength, that can be teleoperated into those types of situations. And being a DARPA project, they're trying to get a broad participation, have lots of people participate in this project writing software, and a very aggressive development schedule. One thing that's holding that back, of course, is that humanoids are fantastically expensive, particularly human scale, human strength, hydraulic humanoids like this. So what we're trying to do to help out here is to develop software on top of ROS and Gazebo, which is an open source simulator. So the thing that simulators can do is they can let you look at the data before the robot's actually ready. So we essentially can write a simulation that says, if there was a robot, it had these shapes, and it had these sensors on it, we can simulate that and then start writing software for it as if it existed. And if we got the API right, and if we got the simulation reasonable, then when you do get the real robot, of course there'll be some tuning and things, but at least, the signs are right. At least you're in the right direction. So Gazebo, this open source simulation platform that many people at the Open Source Robotics Foundation are working on, it can simulate all these different sensors. So we have there on the upper right, the laser scanner coming out of the robot's head. We can simulate those collisions with the world. There's then underneath on the sort of lower left there's a stack of 2 images. Those are the right and left cameras on the robot's head. And you can, it's a little hard to see at this resolution, but they're slightly offset horizontally. And that's actually a geometrically correct projection, so that then everything downstream in ROS can run as if it was a regular camera. And we're doing stereo reconstruction there to generate that 3D point cloud of the vehicle on the lower right. We can also simulate things like the inertial units, the force torque sensors, and the robot's wrists and feet, and so on. So let's do some demos and see if we can get a little more dangerous here. So I'm going to start up the simulator. Everything here I'm showing you is open source, available on the internet. ROS.org is the main kind of portal to the ROS world, but then there's also gazebosim.org for the simulation, or DRC simulation that Google, I'm sure, would take you there also. So let's start this thing, see what happens. This is all very fresh code, so it might be kind of exciting. Okay, so now we have a world with a vehicle in it and with a robot in it. Let's see. Okay, so the interesting thing and the fun thing now is that it's not just a cartoon, there's actually rigid body dynamics running here. This is actually a physical simulation. So you can see the robot is a little bit kind of wobbly, looks a little teetery. That's because there actually are position controllers running, trying to hold that posture. And you can see him kind of waving around a little bit. We just wrote a very, very simple controller as sort of a straw man. We're expecting, of course, everyone to throw away that controller that we wrote, but use the underlying infrastructure and simulation engine to write their own software. So some of the fun things about a simulation, unlike the real world, you can then sort of grab vehicles like your Superman and move them around. You can take things, rotate them, sort of do whatever you want. So I'll use this now to show the simulation. So this window here is sort of a God's eye view. This is not what any robot, I mean, of course we could write much better robot software if we actually knew the data structures and the state controlling this world, but that's not how the real world is. When you write robotic software, typically all you have to deal with are the robot sensors. So you actually don't get this perspective. Instead you get something very different, which we can simulate here. The robot has a laser. Well, actually, let's run first. Nothing like trying to type on a 20-foot screen while everyone's watching you. Okay. Okay, so now let's simplify this thing a little bit. Okay, so here, there's a robot there. All those are little coordinate frames being drawn. You can tell the hands have lots of degrees of freedom because there's a whole bunch of coordinate frames. There's one coordinate frame for each degree of freedom of the robot. So as the robot moves around, all these little coordinate frames would be moving. So again, as mentioned before, this stuff is supposed to be general to many robots. This whole visualization tool was actually written for the PR2 robot at Willow Garage, but has since been used by many things. It really is just looking at ROS messages and putting them in an OpenGL framework. And so that's why it works with any subsystem that you or anyone else will write around the world for ROS-based robots. So this robot is really neat. It has a laser scanner in its head. So we can see that because he's in this sort of simulated infinite plane, all the laser scanners are turning that's its maximum range of 50 meters or whatever it is. So that's kind of boring. So we can look at another feature of this robot. If we look closely on his head, the laser scanner on this particular robot is actually on a spindle that can turn around. So we can start that spindle spinning. Let's see. So now that spindle is turning. And the fun thing is we can simulate all the lasers being projected from that spindle. So if we go back to this visualizer, now you can see that it's essentially carving out a hemisphere. And the top of the hemisphere, that's just the laser's maximum range. It says I didn't really see anything. But if we look closely at what it's showing here, there's the vehicle. It is a simplified collision model. In the gazebo simulator, there's the visualization layer, and then there's the physics layer. So we can plot what's actually happening on the physics layer here. So the visualizer looks cool. The car has lots of different colors and stuff. But unfortunately, it's hard to simulate all those little teeny features. So what we do instead is we have a simplified model to try to keep the simulation speed reasonable. So we can see if we zoom in on the car. The car is sort of made of a bunch of blocks. The only thing we've really modeled closely is the steering wheel, because the robot in this DARPA program is supposed to walk over to the vehicle, sit down in it, and drive it, just like we would drive it. Okay. So now some of the other sensors I mentioned that it has we can look at the camera feeds. So if we go ROS topic list here, just like before, now that the world is much more complicated, there's a whole lot more topics. But we can say, let me look at the, let's see, the right camera from its head. We can take that topic. There's a handy utility called image view. So we're image view. And hopefully this will work. Yeah, cool. Okay, so there's the image stream coming out of the robot's head. It might wave around a little bit as you see the robot kind of wobble when he's standing up. Actually, let's keep that running, because in case he falls down, it gets kind of funny. Let's see this guy. It's the great part of simulators. Okay, so we have pictures. We can then run the stereo pipeline just like a normal robot that actually has cameras. So this is actually what the stereo pipeline is computing. So now this is important to note. This is not just a point cloud that we're generating from the simulator. It's actually we're generating images and then running stereo vision on those generated images. So I can show what that's doing if we go RX graph here. Okay, so this is a lot more complicated than we had before. Oh dear, this resolution is not going to work well. But okay, well, yeah. So this sort of mess right here is the stereo processing stuff in ROS, and that's being used out of the box just as if you had a real robot with two real cameras combining them together. So you can see, just like real stereo vision, it's not quite what you'd hope for. It's sort of wiggly and squabbly, and there's pixelization and quantization artifacts, and that's kind of what you get in the robot. And this is actually pretty good. And so we can corrupt this data more if it needed to be. The other nice thing with the logging utilities, you could just dump all your messages to disk and play them back later. Okay, so let's do some more fun stuff. So this vehicle, like I was mentioning, is supposed to be able to drive a car. So we're just providing infrastructure for this project. We're not actually going to be competing ourselves. Of course, that would be sort of cheating. So so we just wrote some hard-coded. We're not smart enough to write the code for the robot to walk over there. So instead, we can just cheat and make the robot teleport and drop into the driver's seat. So now he's there. Looks sort of like a gorilla in like a circus car or something. Okay, so we can look back at what his sensors are seeing. Let's see, he's kind of dancing around his legs a little bit. So now he's parked in his car, and we should see as the laser spins around, you'll see the dashboard of the vehicle right there. Okay. So because this is a simulator, we can also cheat, and we can just tell the car to start driving forward. So now it's going to put the car in gear, turn the wheels, and then just start cruising around. So now he's just kind of driving around. Okay, so we can then, again, on the real competition, you're supposed to then have the robot slide off the driver's seat, get out of the vehicle, and start walking around. We're not there yet, so we, again, can cheat. We can just kind of yank the robot out of his vehicle and plop him down next to it. So we can just pull him out. There he is. He's probably going to fall over. Oh, there he goes. Oh, ruthless. Leaned up on the side of his vehicle. Look at that. Oh, that is so awesome. Just terrible. So these platforms are like $1 million, right? So this is why it's so fun to do this in simulation. Let's see, let's move this car out of the way so he can properly fall on the ground. Oh, there he goes. Oh. So this is why we love simulators. Yeah. So again, since we're Superman, we can even do crazy things like let's see, let's pick up this car, maybe drive him over here, and now let's let go of the car. Oh. Oh, that's just too gruesome. Well, let's move the car away now. Okay, so let's see. Let's stand him back up again. It makes me feel better. Okay, there he goes. Now the world's better. These are the simulator tools. They're all open. The whole stack you've seen is open top to bottom. Feel free to download. Gazebo is being done on Bitbucket, which is like GitHub, but for Mercurial. Patch requests or pull requests are always gratefully accepted. So let me just go on my last slide here, and I'm about out of time, so we can have some question time at the end here. Let's see, where am I? Okay, that was actually the last one I had. So thanks for your time. I think there's plenty of time for questions now if you want to have some. I'm happy to answer. Try to.
So my question is about support for multi-robot systems. So far you showed only single robot applications, and so can you do anything like that with multi-robots?
Okay, the question is about multi-robot systems. In other words, all the little demos I showed here were of single robot systems, and the question is how do we deal with or can we deal with multi-robot systems? So that's a great question. There were some videos in that sort of collage video that had like every 2 seconds was another robot. There were some pictures in there of people doing that. So it can be done. That's an area of actually intense work right now in the community. A lot of people are very interested in that. So part of the system, you know, as it was architected originally, was made for these very large robots that have several computers on board. And so connectivity was sort of always assured. We always assumed that everyone could talk to the master node that runs the whole like DNS. As you break that assumption, because robots can maybe go, they kind of wander apart and wireless links get broken, lots of things start to break down, as is in ROS. And so there's a lot of people that are very interested in making that work well. One of the things that people do, you can run ROS masters on top of each robot and then have bridges back to sort of a supermaster layer that runs on top. There are implementations of that out there on the internet you can find. But again, that's an area a lot of people are working on right now. That's very sort of fresh research right now. And feel free to contribute. Would love to have your answer in your implementation too.
Yes, I wanted to ask about your plumbing layer, the kind of a message bus type thing. Is that, I mean, you had your own interface description language, but is the underlying message bus something standard, or what open source components do you use?
So right now, we have our own that's rolled in there. Everything's open source, of course, but it is our own. You know, we did this back in 2006, 2007 is kind of when we started going. And then sort of right as we got to like our 1.0 release, Google released the protocol buffers, which is like the same thing. So, you know, as we revise the system and improve it in the future, we're thinking about going that and just using these standard systems underneath. As is, it's a custom thing that's done. It does TCP sockets primarily, but you can also then swap that out for a UDP implementation for things like images where that makes a little more sense. But that's where we are right now anyway. It's a custom implementation, but we're looking as we revise the system to replace that with standard things.
Yeah, so I saw that the endpoints had like HTTP URLs, but in fact it's not really HTTP or...
So what happens is there's actually sort of several different endpoints for each ROS node. One is an XML RPC configuration layer. So there's actually not high bandwidth data that goes there. Instead, that's what you do is you connect to there, you say what are, you know, you sort of negotiate a high bandwidth channel over that. So the HTTP was actually an XML RPC port that gets opened up just for configuration. Nothing goes fast over there.
Thank you.
Yeah.
Hi, I have two questions. The first is which platforms do you support? Do you support Windows as well, or just Linux? And the second one is if I write a module that uses ROS, how do you distribute it so that it builds with Windows, Linux, or all the platforms you support?
Okay, thanks. So the question was two parts. The first is what platforms are supported, and the second is if you write a ROS module yourself, how do you distribute it? Those are great questions. I should have mentioned those in the talk. I didn't. So to answer the first question, Ubuntu is the easiest to use. That's what a lot of people use in the ROS community. We provide, well, I mean, Willow Garage, and we contribute a little bit there. It provides like binary deb packages you can just download and install on top of Ubuntu. There are there's a lot of people out there that use things other than Ubuntu, of course. So there are people using those systems. There are notes on the wiki you can try to follow. I would suggest using Ubuntu if you're trying to just sort of experiment with things out of the box, because it just apt-get some packages and it gets up and running. Other Linux distributions are in various stages of working or not workingness. Mac OS X, there is some support there, but I would just suggest using Ubuntu, actually. So the Windows port is a long ways away. We do lots of multi-process stuff that's sort of just coming from the Unix philosophy of we have 50 processes running, which is It can be done with Windows. I think in time, because so many people use Windows, we should figure out how to support it better. We would certainly welcome any and all contributions toward that goal, but we've swapped our build system now to CMake, and so that was sort of done hoping to get this long-term vision of a Windows build possible. It sort of is just different fundamentally from how people use Windows, so it's tough. In terms of the how do you publish code that you write yourself, we encourage everyone just to do their own distribution. We're not trying to be a gatekeeper of code, just to rather put your code up on GitHub and put a link out there to people and with build instructions, just like anything else. Thanks. Okay, I think we're out of time now, so I'm happy to keep answering questions out afterwards in the hall if that would help. Thank you very much.